Welcome to Episode 5 of the Automotive Cybersecurity Engineering series. Today, we're diving into CAN bus security and attack methodologies. This episode will take you from theory to real-world exploitation, showing you exactly how attackers target vehicle networks. Let's get started! So what will you learn today? We've organized this episode into 5 main sections. First, we'll cover CAN protocol fundamentals. You'll learn about the architecture, message structure, and how arbitration works. Second, we'll explore CAN security vulnerabilities. We'll discuss why CAN is inherently insecure and what prerequisites attackers need. Third, we'll go through attack methodologies. This includes sniffing, injection, fuzzing, denial of service, and replay attacks. Fourth, we'll look at hacking tools and lab setup. You'll learn about tools like Canoe, Wireshark, CAN Utils, and how to set up IC-SIM for practice. Finally, we'll cover defense mechanisms. This includes SecOC, intrusion detection systems, gateway filtering, and network segmentation. By the end of this episode, you'll understand CAN bus security from both the attacker's and defender's perspective. Let's start with a fundamental question. Why is CAN bus so important? CAN became the automotive standard for several key reasons. First, it's low cost because it uses a simple two-wire bus topology. Second, it's real-time with deterministic arbitration, which is crucial for vehicle control systems. Third, it's reliable with built-in error detection using CRC and ACK mechanisms. Fourth, it's multi-master, meaning any node can initiate transmission. Fifth, it has fault tolerance with a bus-off mechanism for failing nodes. And finally, it's widespread, used in over 90% of vehicles since the 1990s. Now let's look at some modern CAN usage statistics. A typical vehicle has 2 to 5 CAN networks, covering areas like powertrain, body control, and chassis systems. Each CAN network connects 20 to 30 ECUs. Traditional CAN 2.0 runs at 500 kilobits per second, while CAN FD can reach 2 to 5 megabits per second in the data phase. CAN 2.0 has a maximum payload of 8 bytes, but CAN FD extends this to 64 bytes. But here's the critical security issue. CAN has no authentication, no encryption, and no sender verification. This makes it a perfect target for attackers. Remember, CAN was designed in 1983 for isolated networks. Security wasn't even a consideration back then. Let's look at the CAN protocol architecture. CAN uses a multi-master bus topology. The physical layer consists of 2 wires, CAN high and CAN low. These create a differential signal that's resistant to electromagnetic interference. Connected to this bus are various ECUs. You might see an engine ECU, transmission control unit, ABS ECU, body control module, gateway, and ADAS ECU, all communicating on the same bus. Here are the key characteristics you need to understand. First, it's broadcast. All nodes receive all messages. Second, arbitration is based on message ID. The lowest ID always wins bus access. Third, and this is critical, there's no source authentication. Any node can send any CAN ID. The security implication here is huge. With no authentication, no encryption, and no sender verification, an attacker who gains access to the CAN bus can impersonate any ECU and send any command. This fundamental weakness is at the heart of all CAN bus security issues. Now let's examine the CAN message structure in detail. A CAN 2.0 standard frame consists of several fields. It starts with a start of frame bit, followed by an 11-bit identifier. Then come the RTR bit, IDE bit, and reserved bit. The DLC field specifies the data length, followed by 0 to 64 bits of actual data. The frame ends with a 15-bit CRC for error detection, an acknowledgement field, and an end-of-frame marker. CAN FD, which stands for Flexible Data Rate, has some key differences. It includes an FDF bit to indicate it's a CAN FD frame, a BRS bit to switch bit rates, and an ESI bit for error status. Most importantly, it supports up to 64 bytes of payload instead of just 8. Now here's where things get interesting from a security perspective. Let's look at the attack points in a CAN frame. First, the ID field can be spoofed. An attacker can impersonate any ECU by using its CAN ID. Second, the data field is sent in plain text. It can be sniffed and replayed without any protection. Third, there's no authentication mechanism. There's no way to verify the sender's identity. And fourth, there's no encryption. All data is transmitted in clear text, making eavesdropping trivial. These vulnerabilities make CAN bus attacks relatively straightforward once an attacker gains physical access to the network. Let's dive deeper into CAN security vulnerabilities. The title says it all. CAN was never designed for security. Let's go through each vulnerability category. First, we have no authentication, marked as critical. Any node can send any CAN ID, which makes spoofing attacks possible. There's no way to verify who sent a message. Second, no encryption, also critical. All data is sent in plain text, enabling eavesdropping and data theft. An attacker can simply listen to the bus and capture sensitive information. Third, no message freshness, rated high. Without timestamps or counters, replay attacks are trivial. An attacker can record a valid message and replay it later. Fourth, arbitration abuse, rated medium. The lowest ID always wins bus arbitration. An attacker can flood the bus with ID 0 messages to perform a denial of service attack. Fifth, broadcast nature, rated high. All nodes receive all messages, making reconnaissance easy for attackers. Nothing is hidden on a CAN bus. And sixth, bus-off exploitation, rated high. By injecting bit errors, an attacker can force specific ECUs into a bus-off state, effectively removing them from the network. The bottom line is simple. CAN was designed in 1983 for isolated networks. Security was not a consideration at all. This legacy design is now a major challenge as vehicles become more connected. Now let's look at the overall attack methodology. There are 5 main phases of a CAN bus attack. Phase 1 is reconnaissance and sniffing. Here, the attacker monitors bus traffic and identifies CAN IDs. They're learning how the network behaves. Phase 2 is message injection. The attacker starts sending crafted CAN messages to see what effects they can achieve. Phase 3 is fuzzing and discovery. This involves systematically testing unknown IDs to find responses and discover undocumented functionality. Phase 4 is denial of service. The attacker floods the bus or forces ECUs into bus-off state to disrupt normal operation. Phase 5 is replay attack. The attacker captures valid messages and replays them to achieve the same effect later. Now, what do attackers need to get started? There are 3 main prerequisites. First, physical access. This could be through the OBD2 port, internal CAN wiring, or a compromised ECU. Second, tools. You need a CAN transceiver like Cannibal or Quasar, a laptop, and attack software. Third, knowledge. You need to understand the CAN protocol. Having the target vehicle's CAN database, a DBC file, is helpful, but not strictly required. Attackers can discover message meanings through testing. Let's start with attack number 1, sniffing and reconnaissance. This is a passive observation attack. The attack objective is to monitor CAN bus traffic for several purposes. First, identify which CAN IDs are active. Second, understand message patterns and timing. Third, correlate IDs with vehicle functions. And fourth, find interesting targets like steering, brakes, or door locks. For tools and commands, let me walk you through the basic setup. First, you set up the CAN interface with a specific bit rate, typically 500 kilobits per second. Then you bring the interface up and start sniffing with the CAN dump command. You can filter for specific CAN IDs if needed, or log everything to a file for later analysis. On the right side, you can see example sniffed data. Each line shows the interface, CAN ID, data length, and the 8 bytes of data in hexadecimal format. For instance, you might see ID 161 with data, ID 166 with different data, and so on. Here are some analysis tips. Look for periodic messages that repeat every 10 or 100 milliseconds. Identify dynamic data that changes with vehicle state, like speed or steering angle. Use physical triggers to help with correlation. For example, turn the steering wheel and see which CAN messages change. Press the brake pedal and observe which IDs activate. This correlation helps you map CAN IDs to physical functions. Now let's move to attack number 2, message injection and spoofing. This is an active attack where we send malicious CAN messages. The attack process has 4 steps. First, identify the target ID. Second, craft the payload. Third, inject the message onto the bus. Fourth, observe the effect. Let's look at some real example attack scenarios. Speedometer. Spoofing. You can target CAN ID 0x166 with a specific payload to display a false speed. For example, sending 00FFFF00000000 might make the dashboard show 255 kilometers per hour even when the car is stationary. Docker unlock command using CAN ID 0x2C1 with payload A50100000000. You can unlock all doors remotely. This is exactly the kind of attack that worries security researchers. The command to inject this message is simple. Can send CAN 02C1 #A5010000000000. The scary part is how easy this is. Once you know the right CAN ID and payload, sending these commands takes just a single line of code. This is why CAN bus security is such a critical concern in modern vehicles. Attack number 3 is fuzzing and discovery. This is systematic testing to discover unknown functions. So what is fuzzing? Fuzzing is sending random or semi-random CAN messages to achieve several goals. First, discover undocumented CAN IDs that aren't in any official documentation. Second, test ECU behavior with unexpected inputs. Third, find vulnerabilities like crashes, errors, or strange responses. And fourth, map out the attack surface to understand what's possible. There are several fuzzing strategies. Strategy 1 is ID sweep. Test all possible CAN IDs from 0x000 to 0x7FF. Strategy 2 is payload mutation. Vary the data bytes systematically to see different responses. Strategy 3 is high-frequency flooding. Send many messages quickly to test for race conditions. Strategy 4 is testing edge cases. Use boundary values like all zeros or all FFs. Here's an important warning. Fuzzing can cause unintended effects. You might crash ECUs, trigger error codes, or even cause physical damage in some cases. Always test in a controlled environment, never on a vehicle that's being driven. Let me show you a simple fuzzing script example. This bash script sweeps through all standard CAN IDs. For each ID, it generates a random payload and sends the message with a small delay. While it's running, you should monitor ECU responses using CANDump in parallel. Pro tip: watch for unusual responses during fuzzing. If you send a particular ID and suddenly see a burst of responses or error messages, you've probably found something interesting. These anomalies often indicate diagnostic functions or hidden features. Let's look at attack number 4, denial of service, or DOS. The goal here is disrupting CAN bus communication. There are 3 main types of DOS attacks against CAN networks. First is bus flooding, rated as high severity. You flood the CAN bus with high-priority messages, typically using ID 000. This prevents legitimate messages from winning arbitration. The bus becomes so congested that normal communication can't occur. Second is bus-off attack, rated as critical. This is more sophisticated. You inject bit errors to force a target ECU into bus-off state. This requires GPIO control, or a non-conforming CAN controller that lets you violate the protocol rules. When an ECU sees too many errors, it assumes it's faulty and removes itself from the bus. Third is resource exhaustion, rated as medium. You send many SecOC protected messages to overload the ECU's CPU. This forces the ECU to spend all its processing cycles on MAC verification, leaving no resources for normal operation. Here's a simple bus flooding example. This command creates an infinite loop that sends CAN messages with ID 0 and all zeros as data. It's brutally simple but effective. The bus becomes completely unusable for legitimate traffic. The impact of DOS attacks ranges from degraded performance to complete loss of vehicle functionality. Imagine if an attacker could disable the ABS system or prevent the engine ECU from receiving commands. These scenarios show why DOS protection is crucial. Our 5th and final attack type is replay attacks. The concept is simple: capture once, replay anytime. The replay attack process has 4 steps. Step 1 is capture. You record legitimate CAN messages, such as a door unlock command when the owner presses their key fob. Step 2 is store. You save the captured messages along with their timing information. Step 3 is replay. Later, at an opportune moment, you retransmit the exact same messages onto the bus. Step 4 is success. The ECU accepts the replayed message as legitimate because it has no way to detect that this is a replay. Let me give you a real-world example of a keyless entry replay attack. First, the attacker positions themselves near the car when the owner presses the key fob to unlock it. They capture the door unlock signal. CAN ID 0x2C1 with data. A5010000. 00000000. Second, the owner locks the car and walks away thinking their vehicle is secure. Third, Hours later, the attacker returns and replays the exact same message using CAN-SEND. Fourth, the result, the car unlocks. There's no freshness counter to detect this is a replay, no timestamp to invalidate old messages. The ECU simply sees what looks like a valid unlock command and executes it. This attack works because CAN has no concept of message freshness. Without timestamps or sequence numbers, there's no way to distinguish between a current command and one that was valid hours ago. This is why SecOC's freshness counter is so important for modern vehicle security. Now let's talk about the practical side, hacking tools and lab setup. Here are the tools every CAN hacker needs, organized into 3 categories. First, hardware. You'll need a CAN to USB adapter. Popular options include Cannibal and Cantact, which are affordable open-source designs. Quasar Leaf Lite is a commercial alternative. Pecan USB is another reliable option. Don't forget an OBD2 to DB9 cable for connecting to real vehicles. Second, software. On Linux, CANutils is essential. It provides commands like CANdump and CANsend. Wireshark with Socket CAN support lets you analyze CAN traffic with a familiar interface. Canoe and Canalizer from Vector are industry-standard professional tools. And the Python CAN library is great for scripting custom attacks. Third, practice labs. ICSM, the Instrument Cluster Simulator, is perfect for learning. It creates a virtual vehicle dashboard that responds to CAN commands. CANtools is a framework for building attack tools. Kayak is a Java-based CAN analysis tool. And SavvyCAN is an excellent open-source option. Let me walk you through a quick start guide for ICSM. First, clone the repository from GitHub and compile it. Second, set up a virtual CAN interface. You load the VCAN module, create a virtual interface called VCAN0, and bring it up. Third, run the simulator. Start ICSIM, which displays an instrument cluster, and controls which gives you buttons to generate CAN traffic. Fourth, start attacking. Use CANdump to sniff the traffic and figure out which CAN IDs control the speedometer, turn signals, and door locks. This practice environment lets you learn safely without any risk to real vehicles. It's perfect for understanding the concepts before moving to more advanced work. Now let's examine a famous real-world case, the 2015 Jeep Cherokee hack by Charlie Miller and Chris Velasek. This was a landmark moment in automotive security. Let me walk you through the attack chain. Step 1. They exploited the cellular connection through Sprint's network. The Uconnect system had vulnerabilities that allowed remote access. Step 2. They compromised the Uconnect head unit, which is the infotainment system. This gave them a foothold inside the vehicle's network. Step 3. They gained access to the internal CAN network. Here's the critical failure. There was no network segmentation between the infotainment system and the safety-critical CAN buses. Step 4. They sent CAN messages directly to ECUs like the engine controller and brake system. Step 5. The ultimate result, they could control steering, brakes, and transmission remotely from miles away. The key lesson here is crucial. No network segmentation between infotainment and safety-critical CAN buses allowed remote attackers to control physical vehicle functions. The infotainment system should have been isolated, but it wasn't. Now let's look at the impact and response. 1.4 million vehicles were recalled. The estimated recall cost was $105 million. This was the first major remote vehicle hack demonstration, changing the industry forever. From disclosure to patch deployment took about 2 months. The defense that was implemented included several improvements. Network segmentation with a gateway firewall to isolate different domains. A Uconnect software update mechanism to patch vulnerabilities remotely. And cellular authentication improvements to prevent unauthorized access. This case study shows that these attacks aren't theoretical. They're real and have serious consequences. Every automotive engineer needs to learn from this incident. Now let's talk about defense. The key principle is defense in depth, using multiple layers of security. Let me walk you through each layer. Layer 1 is physical security. This includes OBD port locks to prevent unauthorized access, tamper detection to alert when someone is trying to access the network, and secure connectors that are harder to exploit. Layer 2 is network segmentation. Implement gateway firewalling to control traffic between different network segments, use VLAN separation to isolate different types of traffic, and apply zone isolation to separate safety-critical from non-critical systems. Layer 3 is authentication. Implement SecOC message authentication codes to verify message authenticity, use end-to-end protection for critical communication paths, and deploy certificate-based authentication where appropriate. Layer 4 is monitoring and detection. Deploy intrusion detection and prevention systems, implement anomaly detection to spot unusual behavior, and maintain comprehensive event logging for forensic analysis. Layer 5 is secure development. Perform threat modeling during the design phase, follow secure coding practices, and conduct regular penetration testing to find vulnerabilities before attackers do. Here's the critical reminder: no single control is sufficient. You need multiple layers of defense. If one layer fails, others should still protect the system. This is what defense in depth means in practice. Let's dive deeper into SecOC, the most effective CAN security solution currently available. SecOC stands for Secure Onboard Communication, and it's part of the AUTOSAR standard. Here's how SecOC works step by step. First, you start with the original CAN message. Second, you compute a MAC, message authentication code, using AES KeyMac algorithm. Third, you truncate the MAC to 24 or 32 bits to save bandwidth. Fourth, you add a freshness counter. This prevents replay attacks. Fifth, you append this to the payload. Sixth, you transmit the secured message. On the receiving side, the ECU verifies the MAC and checks the freshness counter before accepting the message. Here's an implementation checklist to guide you. First, identify which CAN IDs are critical enough to protect with SecOC. You can't protect everything due to performance constraints. Second, select the MAC truncation length, typically 24 or 32 bits. Third, choose your freshness mechanism. Will you use a simple counter or a timestamp? Fourth, implement HSM integration for cryptographic key storage and operations. Fifth, configure SecOC properly in your AUTOSAR stack. Sixth, test MAC generation performance to ensure it meets real-time requirements. Seventh, verify that freshness synchronization works correctly across all ECUs. Now let's talk about the challenges. Performance overhead on low-power microcontrollers can be significant. You're adding payload bandwidth cost. Those extra bytes for MAC and freshness reduce available space for actual data. Key management becomes complex when you have dozens of ECUs. And freshness synchronization can be tricky, especially after events like ECU resets or power cycles. Despite these challenges, SecOC remains the most effective defense against CAN bus attacks. It's becoming mandatory in many new vehicle architectures. Let's wrap up with the key takeaways from this episode. Takeaway 1: CAN was not designed for security. It has no authentication, no encryption, and no freshness protection. The broadcast architecture makes all traffic visible. These are fundamental protocol weaknesses that can't be patched away. They're inherent to the design. Takeaway 2: attack prerequisites are low. Physical access to an OBD2 port or a compromised ECU is sufficient to launch attacks. Low-cost hardware, under $50, and open-source tools make CAN hacking accessible even to attackers with limited resources. Takeaway 3: there are 5 main attack types you need to understand. Sniffing for reconnaissance, injection for spoofing, fuzzing for discovery, DOS for disruption, and replay for reusing captured messages. Each type exploits different CAN weaknesses. Takeaway 4: real-world attacks have already happened. The Jeep Cherokee hack in 2015 demonstrated remote vehicle control. 1.4 million vehicles were recalled. The network segmentation failure allowed the attack to propagate from infotainment to safety-critical systems. Takeaway 5: defense requires multiple layers. You need SecOC for authentication, intrusion detection systems for monitoring, gateway filtering for isolation, and physical security for access control. No single solution is sufficient. You must implement defense in depth. Thank you for watching Episode 5. You now understand CAN bus security from an attacker's perspective. You've learned how these attacks work, and more importantly, how to defend against them. In our next episode, Episode 6, we'll explore automotive Ethernet security and the SOAM IP protocol. We'll cover TSN, AVB, MACsec, and the future of in-vehicle networking. Ethernet is becoming increasingly important in modern vehicles, bringing new security challenges and opportunities. This is part of the Automotive Cybersecurity Engineering series. If you have questions or want to discuss these topics further, feel free to reach out. Thank you, and see you in the next episode.